Hi, everyone. Today we're going to be talking about the concept of impulse. An impulse is something that an object puts onto another object in order to cause its momentum to change. The word impulse means a change in momentum. Let's look at an example of where an impulse might be a relevant concept. If you take something fragile like an egg and you drop it onto the floor, you know it's probably going to break. But if you were to drop two eggs and one of them you drop onto the floor and one of them you drop onto something soft like a pillow or a sponge or some other soft material like a towel, something around your house, there's a chance that that egg will actually be fully intact even when it lands and comes to rest. So, what is the physical difference between these two scenarios? In order to look into this, we actually went ahead and did a little demonstration at home here. And I'm going to play the first little section of this video where we actually dropped an egg onto our kitchen tile, and then we dropped another egg onto a pad of foam. So let's start our video here. And you can see on the left, there's no foam. On the right, there's about 3 or 4 centimeters of foam. And we'll drop the eggs once at normal speed. And that will play 2 more times so you can see it again. And again. So as you probably would have guessed, the egg without any extra padding on it does break when it hits a hard surface. Not surprising anyone there. But what is the physical difference between these two outcomes? Well, one thing that we can definitely say is that the eggs originally have some momentum as they're traveling towards the floor, and they gained that momentum as a result of gravity pulling on them. When they hit the floor, they have a change in momentum. They go from having a lot of momentum to none at all by the time they're stopped. So there is a change in momentum for both eggs as they come to rest. And assuming that the eggs are the same size and they were traveling at the same speed before they hit the ground, they're probably going to have the same change in momentum. But do they experience their changes in momentum in the same way? Probably not, because we see that there are different outcomes here. So that's what we're going to be looking into here when we talk about impulse, which, as I said before, means a change in momentum. We're going to go through the math here of what impulse is and how to calculate it, and it should answer this question of why does one egg break and the other does not. So first thing I'll note here is that there's a delta symbol next to the P symbol, which we would use to represent momentum. So if P is momentum, what is delta P? Well, that means a change in momentum. The delta symbol means you're changing from an initial state to a final state. So if you see delta P, that's equal to the final P, final momentum, minus initial P, initial momentum. This goes for all variables. So there could be delta V, delta P, delta T. Deltas are going to be all over the place in this discussion today. So what is the equation for momentum? Just plain old momentum. It's P equals m times v, or the momentum of an object in motion equals its mass multiplied by its velocity, how fast it's moving. So if this is momentum, what would be the formula for a change in momentum? Well, it could be delta P, change in momentum, equals delta m times v. That would say that something might gain momentum if it gained mass. Now, does that logically make sense? Well, yeah, if there's an object that's traveling at some speed and it suddenly gets larger, it's going to have more momentum because more mass means more momentum. But this isn't really realistic because when you kick a soccer ball or walk and then suddenly start to jog, your mass doesn't really change. It's physically possible, especially at the atomic level, but macroscopically, we don't really see this type of motion happening where objects that are traveling suddenly get more or less massive. So this is not going to be a formula that we use, even though it logically makes sense, because it's just not realistic to our everyday experiences. So that could have worked, but not very useful. Instead, we're going to think about a change in momentum being the result not of a change in mass, but a change in velocity, because that's a lot more sensical. When you're walking down the street and then you suddenly start to run because a cool song comes on in your headphones or something, your momentum changes, not because you got bigger or smaller, but because you sped up. So that gets the Mr. Cowell seal of approval. That's going to be your formula for impulse, which is the fancy word for a change in momentum. So there's a formula for a new quantity, a new property that we haven't seen before. So let's see an example of how we might use this. Let's say you take a tennis ball and you throw it against the wall. What's going to happen? Well, it's going to bounce off the wall and come back at you at some equal or lesser speed. So You could say in this case that the wall puts an impulse onto the tennis ball. It causes it to change its momentum in some way. So let's do a really quick physics problem that shows how impulse would be used. Let's say that we know the mass of this ball, and let's say that we know the initial and final velocity of that ball. From the initial and final states, we can figure out what delta V was for the ball, and we know what mass of the ball is, so we can put those two properties together to figure out what the delta P of the ball is. What is the impulse that was put onto it? Let's do that problem. The impulse that the wall puts onto the tennis ball is equal to its mass multiplied by its change in velocity, its delta V. We said this before, but delta V or delta anything means the final state minus the initial state. So I'm breaking that down there. And now let's plug in our numbers. The impulse is going to be equal to 0.055 kilograms. Notice that I was given 55 grams and I had to turn that into the base unit of mass, which is kilograms. So I did a little conversion there. Multiplied by the final velocity of the ball. And hey, there's a negative in here. You might not have seen that in the formula because it wasn't there, but the final velocity of that ball is negative 6.2 meters per second. Why the negative? Well, that's me showing mathematically that the ball started going one way, but at the end it was going the opposite direction. In physics, we have to define directions with positives and negatives so that our math turns out correct. Towards the right means positive, towards the left means negative. So back to our problem. The final velocity is negative 6.2. And then our formula says minus initial velocity. And in this problem, that was positive 8.4. So those negatives are important to keep track of, obviously, because they're going to change your answers. You put all those numbers together, and your final answer for how much impulse the ball received is negative 0.82 kilogram meters per second. So the unit of impulse is the same unit as momentum. So why is that? Most properties have their own unique unit. Well, it's because impulse isn't really its own unique idea, like momentum and mass, or velocity and distance. Impulse is very similar to momentum because it's just a change in momentum. I can tell you that my height is 6 feet, and in the last 10 years, maybe I've gained 1 inch of height. So I could use inches to describe my height or my change in height. Similarly, momentum and impulse have the same unit because impulse is just a change in momentum. Last thing about this answer before we move on, it's negative 0.82. What does that mean for what happens to that ball? Well, the wall made the ball go in the negative direction. It forced it to not go more positively, but it forced it instead to go more negatively. It ended up going that way instead of that way. So the wall had a negative effect on the ball, not like a good versus bad, but negative meaning to the left. So there's an example of a problem with impulse. But there's something else about impulse that you should know that's actually what makes it very useful other than just solving physics problems. And this is going to be the more important part. So remember the concept of acceleration? I'm going to bring back some old concepts here in order to do some really funky math. Acceleration means that you either are speeding up or slowing down. And there's a formula to calculate how much acceleration an object is using when it's speeding up or slowing down. Like when you're in a car and you hit the accelerator or the gas, your car goes faster. But how much faster? What is the rate of acceleration? Well, this is the formula that you would use to calculate that. You would say that the acceleration of the car you're driving, or in this case, for the problem we just did, what is the acceleration of the tennis ball after it hits the wall? That would be its change in velocity divided by the change in time, or how long it took for this acceleration to occur. So I'm going to take that old formula and I'm going to rearrange it, and you'll see why in a little bit. I'm going to rearrange it to solve for change in velocity. So you can see how I did that. I multiplied by delta t on both sides of that formula, and that resulted in this formula becoming acceleration multiplied by delta t, change in time, equals delta v, change in velocity. So why did I do that? Well, I'm going to smash two equations together here to make one that's new and very useful to us. I'm going to combine the formula that I boxed out in green with the one in brown that I just made by rearranging an old equation, and I'm going to put those together. Here's how I'm going to do that. I'm seeing that there's a delta v in the green formula, the one that calculates impulse, and I'm seeing that there's a delta v in the brown equation, which was related to acceleration. Well, in physics, if you see a variable in a formula and you know how to solve for that variable in a different formula, you can actually plug into one formula what that variable is equal to in the other one. Want to see what I mean? Here's a new version of that green boxed out formula. what I've done is I've replaced delta V with what delta V is equal to or equivalent to. In that Brown formula, it says delta V equals A times delta T. So I put in A times delta T instead of writing delta V because those are equivalent things. They're equal to each other. So why did I do this? This seems like a lot of extra thinking and work, and we already have a formula for impulse. And so it seems like this video should be over and we should be done. But like I said, there's a really important use for impulse that we're just about to get to, but we're not quite there yet. So stay with me here. I now have a formula that says impulse, or change in momentum, or delta P, equals mass of the object multiplied by the acceleration of the object, the rate at which it's changing what it's doing, multiplied by delta T. Now again, this delta T, what the heck is that? Well, in the case of the tennis ball hitting the wall or being bounced off the ground, delta T represents the contact time. Contact time is the amount of time that an object spends being pushed or moved or bounced off of something. You might not realize it because in our everyday experiences, when we bounce something off the ground or the wall, it seems to happen instantaneously. But in reality, if you use slow motion cameras, you can see that it actually takes some amount of time for objects to bounce. It might just be a few milliseconds, but it's not zero. It's some amount of time. So that's what the delta T in that formula represents, the time that the ball spends in contact with the wall or ground or whatever is giving it an impulse. So now we're at this point where we have this big ugly equation with a bunch of stuff in it. I'm going to clean it up using another similar strategy to what I did before. Remember Isaac Newton's second law of motion? Yes, of course, Mr. Cowell. I remember that formula exactly. Well, you know what? You actually could memorize it fairly easily because it's one of the most common and simple equations in physics and one of the most universally useful ones. It says the net force put onto an object, or just F, equals the mass of the object multiplied by the acceleration that the object is experiencing. Let's do the same thing that we did before, where we smash two equations together to make something new that could be useful to us. I see that in that formula I made, where I smushed the two formulas together, there's a m that would be multiplied by an a. And do you see what's in Isaac Newton's second law of motion? There's an m times an a. Well, what is m times a equal to? It's equal to F, the force that is put onto an object. So I just substituted in what m times a is equal to. Instead of writing m times a, I wrote F. So now I've got this new formula that also calculates the impulse that something puts onto an object, the oomph that it transfers, the change in momentum that it causes. And this equation for impulse is based on completely different variables. So it seems kind of silly that we would need two formulas for the same thing. I mean, if you already have one formula and you know how to calculate impulse, why do you need a second one? Well, there will be some circumstances, and actually most circumstances, where you might not know the mass of an object, and you might not know its initial or final or change in velocity. But you might be told how much force is used to move it, and you might be told the contact time, how much time is spent where the two objects are interacting. So in a situation like that, this is the formula for impulse that you would use. So this formula also gets the Mr. Cowell seal of approval. Now that we have these two, we actually have a three-part formula, which is pretty uncommon in our class. And it says that delta P, or impulse, or the change in momentum of an object, is equal to either, meaning you have choices of how you solve for this, it's either equal to the mass of the object multiplied by its change in velocity, or it's equal to the force applied to that object multiplied by contact time. So we have this three-part equation, and that's awesome because this makes us extra flexible. We get to choose now how we solve our problems based on the types of information we're given. If we're not told mass, no big deal. We can use the other part of the formula, plug in force and contact time, and solve for impulse that way. Likewise, if we're not given force or contact time, we could use mass and change of velocity. So this is good. Longer equations actually end up being usually more useful than the shorter ones because you get choices like this. So now that we've seen that, let's go back to this eggs example because I never quite got to answering this question of what's the difference between the two. And now in order to answer that question, I'm going to play the rest of this video, which we didn't get to see. So we're picking up kind of where we left off. We saw the eggs fall and drop, and now we're going to slow it down to 8 times slower than normal speed. So you can see that the egg without the padding broke, and the egg with the padding did not break. Let's see that again. And I want you to try to see if you can notice the difference in what happens to them right at the moment that they land. The egg on the right, believe it or not, actually takes more time to initially slow down before it bounces back up. Now it's being slowed down 80 times. This is 80 times slower than real speed. Try to see that the one on the right takes a few frames to slow down, whereas the one on the left stops immediately and brakes. Could you tell? It takes about 2 or 3 frames. So we're going to look at that again, and it's going to freeze right before the eggs actually hit the ground. So this is the last time we'll play this through. So again, the footage here is going to freeze right before they hit their respective surfaces. And this is 0 frames in this video of contact time has happened. We'll move forward 1 frame, and already the egg on the left has started to break. So at that point, it's no longer in motion as one cohesive object. We'll go forward to 2 frames, and the egg on the right is actually still kind of in the process of slowing down. The egg on the left is just like breaking into a million pieces now. Let's go forward to the 3rd frame, and we can see that now this egg is actually starting to go back up. So it was somewhere in between frames 2 and 3 of this slow motion footage that the egg on the right came to rest. So we're going to estimate it was about 2.5 frames, 2.5. So what can we do with this information about frames? This isn't really like a unit of time we're used to using. Well, based on the fact that the footage that I was filming on a smartphone was filmed at 240 frames per second, we can figure out that the contact time that these eggs had with the ground before they came to rest was 4.16 milliseconds for the egg on the left and 10.42 milliseconds for the egg on the right. So what are we going to do with this information? Well, now that we know a physical difference between the egg on the left and the egg on the right, we can use our knowledge of impulse to figure out how these time differences would play a role. So here's that scenario that I laid out before, without all the motion to distract us, just the diagram of what went on. We can say that both of these eggs experienced the same amount of impulse because they were moving and then they weren't. And that's identical for both of them. So they both had the same amount of change of momentum. But we asked, do they experience their impulse in the same way? And the answer is no. The contact time with the floor as they come to rest was different for these 2 eggs. It was different by a factor of 2.5. So that actually makes the forces on those eggs different as well. This was the really important point that I was talking about before that makes learning this equation so useful, is because we're now going to be able to understand a lot of things in your life and in your world that are based on this concept. So in this case, the egg that landed right on the ground on the hard tiles or in the wood in this diagram, that one felt a very, very strong force in a short amount of time. When those 2 numbers multiply together, it equals the impulse that both eggs felt, because those are identical values. But the egg on the right took a longer amount of time to slow down before it bounced up and did other stuff. And so that long amount of time, that large value for time, needs to multiply by a small amount of force to still equal that identical impulse value. So in this case, the egg on the pillow, it felt a tiny force for longer periods of time. Now, eventually it adds up to the same amount of force that the other egg felt, but it gets to take little teeny tiny bites of force as time goes on. So it feels little pushes over time instead of one big push. And that's really important. If you can lower or increase the contact time, you dramatically change the force that you're exposed to. This is the core principle that keeps you safe in a car in the event of a collision. When you get in a car crash, unless you drive a really, really old antique car, there are things like airbags that will slowly bring you to rest as you crash into something rather than having you slam into the wheel and immediately stop. If you can increase the amount of stopping time when you're in a collision like this, what you'll do is you'll decrease the amount of force that's put onto you and your passengers. This is essential for keeping you safe, especially when you're traveling at very high velocities. So clearly this concept applies to technology, but even in the natural world, this applies. Anytime you jump or move around, you are causing your momentum to change. In other words, you put impulses onto the ground and the ground puts impulses onto you. And so this concept applies to just basic motion too. How do animals like us or cats, who are famously good at landing from jumps, how do they cushion their fall? Well, they bend and compress their body almost like a spring that's being squished. And as they do that, They are lengthening the amount of time that they are spending to stop. And as a result, they are lowering the amount of force that they feel every second or millisecond. So this is a really clever instinct that we have, that we just somehow biologically know that if we can bend and slowly stop instead of quickly stopping, we can avoid injury. Imagine landing from a jump with your knees locked instead of bent. That could result in an injury much more easily than a normal landing could. So this applies to technology, it applies to nature. You're going to see a lot of places in your life now where you'll notice things slowing down gradually as a result of bends and compressions like this. So that's all well and good, but we still need to be able to solve physics problems in this class based on the concepts that we learn about. So of course, I want to show you an example of a few practice problems that you would see that relate to impulse. So I've got a GIF here of a ball boy who's retrieving a tennis ball during a match, and he accidentally trips and slams into the wall. Maybe you've seen this GIF before, and I've turned it into a physics problem. So here's part A. There's going to be 3 parts, and we'll quickly go through all of them. A 60-kilogram boy trips and face plants into a wall. His initial speed of negative 3 meters per second changed to positive 2 meters per second after the collision or post-collision. What impulse did the wall apply to the boy? Okay, so we have a formula for impulse. In fact, we have 2. And the one that's going to be more useful here is impulse equals mass times change in velocity. You may recall there's another part of this formula that says impulse also equals force times change in time, but we're not given that information. So we're going to use this version of the impulse formula. So I need to know the boy's mass. I need to know his change in velocity. And change in velocity, again, just means final velocity minus initial velocity. That's what delta, or change in, always means. Final state minus initial state. So let me plug these numbers in. The mass of the boy was 60 kilograms. The final velocity of the boy was positive 2, and the initial velocity was negative 3. And you might notice that when he's originally running, he's going to the left in this particular GIF, and that's why I chose to call it negative 3 at the beginning and positive 2 at the end. So putting all those numbers together, you get 300 kilogram meters per second of impulse that the wall put onto him. Notice this is a positive value because the wall made him go more to the right instead of more to the left. So that's part A. Here's part B. The boy was in contact with the wall for 0.05 seconds. How much constant force was the wall applying to him during this time? So here's the first example of a problem that's giving us contact time. It's telling us the fraction of time that this boy was touching the wall while it was making him go from this way to that way. So what are we going to use here? Well, they're asking for force. They're giving us contact time. And the only formula that we know of that includes those 2 things this whole year so far is the one that we learned in this video that says impulse equals force times contact time. And we don't seem to have all of these things. We're asked for force, we are given time, but we don't have change in momentum, or do we? If you look up to part A, we actually just solved for the change in momentum that this boy's going to experience. Impulse means a change in momentum. So we actually do know everything we need for this problem. Now it asks for force, so I'm going to rearrange the equation quickly to solve for force by dividing both sides of the formula by time. So now that we've done that, we're ready to plug our numbers in. The change in momentum of the boy was 300 kilogram meters per second, and the contact time was 0.05 seconds, which gives us a final answer of 6,000 newtons. That's like the amount of force in a punch. And you can see that the boy kind of looks like he's been punched by that wall as he slams into it and moves the other way. So that's one example of a physics problem that involves impulse. And now I'm going to give you a slightly more complicated one, but only slightly. That was 2 parts. This one will be 3 parts. Part A, a 65-kilogram fisherman is bucked by an irate sheep. If the fisherman was initially at rest, but moved at 4 meters per second after being struck, what impulse did the sheep put onto the fisherman? Okay, so we're being asked what impulse the sheep put onto the fisherman. We're being given his initial and final velocities. His final velocity is 4, his initial is 0, and we're given his mass. So this is the formula that we're going to use because we have all this information. So delta P equals m times delta V. Let's plug in his mass, which is 65 kilograms, and his final velocity is 4, and his initial velocity is 0 because they say at rest. That means no velocity. Putting those numbers together, we get an answer of 260 kilogram meters per second. That's how much impulse the sheep put onto that guy. It's the oomph that it transferred into him. You can definitely see that oomph playing out in the GIF. Part B. For how much time was the sheep in contact with the fisherman if it applied a constant force of 1,200 newtons, 1,200, as some say? Well, let's see. Okay, so they want to know how much time there was, the contact time between the two objects, and we're being told the force. So this is kind of similar to part B in this last problem. So right away, we're going to say, okay, we need the formula that includes force and time, because those are the two things being offered up here. And they're asking us to solve for time. So I'm going to solve for time in this formula by dividing both sides of the formula by force. And doing that makes it look like this. Delta T, or contact time, equals the change in momentum divided by the force. So they're saying that the sheep applies a constant force of 1,200 newtons. So that's what I'm going to plug in for F. But what am I going to plug in for delta P? Well, remember, in part A, we already solved for delta P. We solved for the impulse that is put onto the fisherman. So we can reuse that information like we did before. So now my final answer is going to come from these two numbers. The time that the sheep was in contact with the man was 260 units of momentum divided by 1,200 units of force. So putting those numbers together, we get an answer of 0.22 seconds. So just a fraction of a second. That makes sense, and it's a realistic answer because when things collide, usually they're not touching for like a year or even like 5 seconds. Usually they collide for less than 1 second, one at most. So 0.22 is a realistic answer. Now part C, this is the final part for today. The sheep was moving at 5 meters per second before the collision and is moving at 0.5 meters per second after the collision. What is its mass? This is a bit of a harder problem, but I'm going to guide you through it. They're asking for mass, so we definitely have to use the formula that has mass in it. So we can't use the one that we used in part B that doesn't have mass. So we know automatically we're going to use this one, but how are we going to use it? Well, we're told that the sheep has a change in velocity because it goes from 5 meters per second, really fast, to 0.5 meters per second. It's almost at rest. So that's a change in velocity. And the sheep has some amount of mass. We're going to need to calculate what that mass is. So we have to assume that there's also a delta P for the sheep, just like there was a delta P for the man. If the man had a change in momentum, where did that momentum come from? It came from the sheep. So I'm actually going to flip this equation around to solve for the thing that they asked me for, which is mass. And it says mass equals change in momentum, or impulse, divided by delta V, change in velocity. And I'm going to plug in the information for the sheep, not for the man, because they're asking me about the sheep. So what are these numbers? Well, the delta P I'm plugging in as negative 260 kilogram meters per second. Why am I plugging in a negative number? Where did that come from? Well, remember in part A, we figured out that the fisherman received that much momentum. He gained 260 units of momentum from the sheep. So where did that momentum come from? It came from the sheep. The sheep had to give it away. So now that we're talking about the sheep, we can acknowledge that the sheep lost that much momentum. And then we divide by the change in velocity of the sheep. The final velocity of the sheep is 0.5 meters per second, and the initial velocity of the sheep is 5 meters per second. So we put those numbers together and we end up getting an answer of 58 kilograms. That's a pretty realistic answer because that sheep is a little bit less massive than the man, which makes sense and makes me think this is probably the right answer. So that was a pretty advanced problem, and we got through a lot of stuff today, and I hope the concept of impulse is something that you'll be able to see in your everyday life. Pretty much anytime an object starts moving or stops moving or changes its motion, you're going to be able to think about impulse and things like increasing time in order to decrease force. So I hope you start to see this in your everyday life. That's it for me today. I'll see you around.